program I wrote to show things about how to draw unit balls of various different metrics because a student asked me this. So I'm assuming you are taking a course on metric spaces and know what a metric is as a way of measuring distance between 2 points. Let's see, here's a daisy, here is a point, here's another point, there is a line between them. We're going to measure this distance. If we had a little ruler, my program doesn't print out the distance, but anyway, there's the distance. One thing about a metric is that a metric must satisfy distance from A to B is the same as the difference from B to A, and the distance from A to B is less than the difference from A to C and C to B. So this distance here is less than going this way. And this metric is just like, a metric is a way of measuring distance. This is like distance as the crow flies. But you can't always fly like a crow, so there's lots of different metrics. Here is a taxi cab metric. Oh, I'm going to draw a picture of allowed paths. So this is like a taxi on Manhattan, I don't know, somewhere going along the avenues and boulevards or whatever you call them. And you're only allowed to go either horizontally or vertically. In this case, as long as this middle point C is between these 2 points, is actually, you don't have to detour at all to get to any other point on the route. This path here, and some of these 2 paths are going to be the same. But anyway, it still satisfies this so-called triangle inequality. So this is a metric where the distance between 2 points is the sum of the y coordinates and the sum of the x coordinates. What I wanted to also do with these things was draw little unit balls. So this distance from the center point to the outside point is unit distance. If we say we travel at, like, I don't know, 1 mile an hour or whatever, then they're 1 hour away and 1 mile away. So I can kind of talk about time and distance in the same way. So this, if you're thinking about this as kind of where you can travel to, this is all the points you can travel to with a 1 hour from this point using the taxi cab metric. So you're going along your taxis on these streets. Furthest you can get an hour somewhere along this line. Of course, it's not really, the metric doesn't really just restrict you to these particular paths. A metric restricts you to just going some vertical path and some horizontal path, whether or not it is exactly along these lines. Okay, so this is what we call the unit ball in this metric. The usual Euclidean metric, or like as the crow flies, looks like this. By the way, here I've done my sort of allowed paths as just a grey area because there's no restriction on our paths, really. We don't think of a restriction for this Euclidean metric. Let's do another metric. There is a railway metric. Our allowed paths are basically lines that go to, say, London. Unfortunately, on the British Rail, you always have to go to London to travel from a town, say, out here to a town here. Okay, well, this is what we're supposing with this metric. I should put these, let's see, let's put one of these points away. Oops, daisy. Okay, and that is my unit ball. Looks like a line, I'm going to call it a ball, about this little yellow point. Okay, so these 2 points, in order to get from this point A to this point B, you have to go through London unless they're on the same line. And then, of course, you don't bother going all the way to London back out again. So this is sometimes called the sunflower metric on various different countries' rail networks. So anyway, the unit ball here, so this is like imagining the distance you can get to with an hour's travel. So you can go either further away from the middle or you can go close to the middle. Now, if that point was supposing that point is all the way at the origin, then the points you can get to are just within an hour. It's just this circle shape. The blue line, whoopsie daisy, the blue line is points which are half an hour away. So let's move something like, I don't know, this. So this point here, you can go all the way to the middle and back out again. So within an hour, you can get to any points around here, any points within this region. Or you can also go away from your starting point. That's your starting point, this little kind of yellow dot. So you get half an hour, you'll get there, and an hour, you'll get there, or you can go towards the middle. So these points here, these kind of red, orange, and so on, those points all show a little, what we call unit ball, even though it doesn't look like a ball. By the way, these lines of points you can get to from this middle point ought to be infinitesimally thin. They ought to have zero thickness. It ought to be that even if you're a teeny tiny bit away from this line, you're going to have to go all the way into the middle and back out again. But because you can't see lines that are infinitesimally thin, I have to give them a little bit of thickness. So anyway, let's put these around here. So as I say, some people call this a, what do you call it, sunflower metric, because it kind of looks a little bit like a sunflower, I suppose. Oh yeah, and here's our points. Let's put, oh yeah, sorry, some of these, here's our third point. So these 3 points don't have a little unit ball around them. So I can try and think about ways to get from A to B to C. And with this particular metric, unless the point, whatever C, is directly on that path, you're always going to have to make quite a detour. So you can see the triangle inequality definitely holds, because it's going to be quite a bit further to go from A to C and then from C to B. Let's look at a different metric as well as the sunflower one. There's the jungle river one. This, let me put some of these points away over here. So my points revert to little circles when I put them away, just to keep them out of the way. So in this jungle river metric, we're imagining we're living in the jungle somewhere, and the only easy travel route is along the river, which is this line here, which is the x-axis. So, whoopsie daisy, but I guess there's some sort of tributaries that go from the jungle down to the river. So the only way you can travel here is if you go down to the river, along the river, and then back out one of these tributaries. So to get from A to B, the distance in this metric is this sum of this y coordinate and the y coordinate of the other point, and the difference between the x coordinates. And if you look at a unit ball, so this point will show unit ball, you can see that if you've got a little point here, you can either take an hour going out this sort of tributary, or you can go to the river and go along the little river and then go out again. So you can go to all the points in this region. So if you're a long way from the river, the only points you can get to within an hour are in this little kind of strip on this particular sort of tributary. Whereas if you're closer to the big main river going through the jungle, then you've got a bigger area you can get to. Let's see, we've also got oval shapes. This is just a sort of distortion of the ordinary Euclidean metric. So in this case, it is easier to go in the y direction than it is to go into the x direction. I don't know why, but for some reason I've decided it's easier. So I'm not quite sure what that corresponds to physically, but it just means the balls are a kind of funny shape, but the lines are the shortest paths between 2 points are just still straight lines. So here we've got distance between A and B is less than the sum of these two distances. Triangle inequality still holds. The only thing is, in this metric, the distance you see of the point from A to B is not going to be the same as the distance you'd measure if you just used your usual Euclidean metric. You're going to have to use a slightly different formula. So I think, and then by the way, you can just have background being kind of a black background, or you can have allowed paths. I've made the allowed paths here just all completely grey, because here, like as the crow flies, just the crow for some reason has more difficulty in the x direction than in the y direction. But basically, there's no restraints. Whereas for the jungle river metric, you have to go kind of either horizontally or vertically if you're not at the x-axis. For the railway metric, you have to go on these radial lines, and for the taxi cab metric, you have to go on this grid. So I hope this is useful for helping to understand a little bit about metrics and how to draw unit balls. You can always go away and make up all kinds of other scenarios, like perhaps you've got a country where there are not only 2 main rail hubs, but perhaps 2 cities. What do you think the unit balls would look like in that case? It may obviously depend on how far apart those 2 cities are. And all kinds of other games you can play on, making up tons and tons and tons of interesting metrics and having fun to see what sort of pictures you get. So send me your favorite metric on the real plane R2. Maybe I can plug it in, or you can let me know where I can find some other ones. Okay, bye for now.